Einstein was the one who interpreted the photoelectric effect by introducing the following hypothesis. All monochromatic radiations of frequency nu are formed of energy packets or photons. The photon is a particle that has no mass, that moves with the speed of light. It is neutral, that it has no charge. It carries a well-determined value of energy equals to h times nu. H is a universal constant called Planck's constant. Its value is equal to 6.63 times 10 exponent minus 34 joule seconds. Nu is the frequency of the monochromatic radiation, which is equal to C over lambda if the radiation is moving in vacuum. If the radiation moves in a certain medium, the speed of light will change, and so will the wavelength. Then every photon of a monochromatic radiation carries or transports the same energy h nu. And since the frequency of radiation is independent of the medium, then the energy transported by a photon is independent of the propagation medium. When radiation illuminates a certain metal, the photon gives all its energy to the target electron, and as a result, the photon disappears. The electron gains the energy of the photon, that is h nu, so the electron uses this energy in order to be liberated from the metal. The energy used by the electron to become free is W0. The remaining part of the photon's energy is transformed into kinetic energy of the electron. Hence, the electron leaves the metal with a maximum kinetic energy. Then the energy of the photon, that is equal to h nu, is completely absorbed by the electron. The electron uses it to become liberated from the metal. The electron uses part of the photon's energy, that is equal to W0, to become liberated from the metal, while the remaining part transforms into a maximum kinetic energy. This is only true if the photon's energy is greater than the extraction energy of the metal. In the opposite case, when the photon's energy is less than W0, the photon is unable to extract an electron from the metal, and as a result, the photon won't be absorbed by the electron, and the electron will stay in the metal. The photoelectric effect won't be realized. Hence, for the photoelectric effect to occur, the energy of the photon of a certain monochromatic radiation that illuminates the metal must be greater than the extraction energy. In the other case, the photoelectric effect won't occur. Einstein's hypothesis can interpret the experimental observation of the photoelectric effect that occurs when the wavelength of the radiation that illuminates the metal is less than a certain value called the threshold wavelength, or when the energy of the photon is greater than W0. When the energy of the photon is greater than the extraction energy of the metal, the photoelectric effect will occur. So Hc over lambda has to be greater than W0. We notice that lambda should be less than Hc over W0. the wavelength is less than a certain value that has dimensions of a wavelength. So we can denote it as lambda 0. Hence lambda should be less than a certain value called lambda 0, where lambda 0 equals to hc over w0. Einstein's interpretation resulted in lambda less than lambda 0. Hence the theoretical study agrees with the experimental one. Moreover, the interpretation had shown that lambda 0 depends on the metal since it is equal to hc over w0, and w0 is the work function of the metal. To facilitate this expression, we can write w0 as hc over lambda 0. Now if you look at this expression, it is very similar to the energy of the photon that is equal to hc over lambda, since the extraction energy is also hc over lambda 0. Note that this formula should be memorized. Then the expression giving the threshold wavelength as a function of the extraction energy is given by this formula. In the appearance of the photoelectric effect, we always have that the energy of the photon is greater than the work function W0 of the metal, and as a result, H frequency or nu should be greater than W0. Then nu greater than W0 over H. We can also denote W0 over H by nu 0. So the frequency has to be greater than a certain value that has the dimensions of a frequency as well. So nu 0 equals to W0 over H, or W0 equals to H nu 0. Nu 0 is called the threshold frequency of the metal. Note that nu is greater than nu 0 and lambda is less than lambda 0. In this case, the photoelectric effect will occur. Nu 0, lambda 0, and W0 are characteristics of the metal. Keep in mind that all radiations are formed of photons. Each photon carries an energy that is equal to the energy of the photon is equal to h nu. Nu is the frequency of the radiation that illuminates the metal, and h equals to 6.62 times 10 exponent minus 34 joules second, which is Planck's constant. To achieve the photoelectric effect by a certain metal, the energy of the photon has to be greater than the work function of the metal. The work function of the metal is the minimum energy capable of extracting electrons from the metal. It is a characteristic of the metal. When the energy of the photon is greater than W0, the photon gives all its energy to an electron. The energy of the target electron becomes equal to the energy of the photon, which is equal to h nu. Now to leave the metal, the electron needs an energy equal to W0, and the remaining energy transforms into a maximum kinetic energy. This maximum kinetic energy will be acquired by the electron after leaving the metal, when illuminated by radiation of frequency nu. The radiation that is suitable to achieve the photoelectric effect should have a wavelength that is less than lambda 0. Lambda 0 being the threshold wavelength of the metal. Lambda 0 can be calculated by the formula W0 equals to hc over lambda 0, or the frequency of radiation should be greater than the threshold frequency. That is also a characteristic of the metal, where its value can be found by using W0 equals to H nu 0. The photoelectric effect shows another aspect of light other than the wave aspect. It shows the corpuscular aspect of light. It defines light as being formed of energy quanta, or packets, or photons. The wave aspect of light was unable to interpret the photoelectric effect. The wave aspect considers light to be an electromagnetic wave. When an electromagnetic wave reaches the metal surface, over time, the electron will absorb enough energy until it is greater than the work function of the metal. Then, in this case, the radiation will be able to extract an electron from the metal. But this contradicts with the experiment. The photoelectric effect experiment had shown that this phenomenon is quasi-instantaneous. For a light whose wavelength is less than lambda 0, it is unable to extract electrons almost instantly from the metal. If lambda is greater than lambda 0, no electrons will leave the metal no matter for how long will the metal be illuminated. Hence, the wave aspect was found to be unable to interpret the photoelectric effect. The photoelectric effect is interpreted by the corpuscular aspect of light. Consider the following application. A monochromatic light of wavelength lambda equals to 0.48 micrometers illuminates a potassium cathode of threshold wavelength lambda 0 equals to 0.54 micrometers. We're going to schematize the problem. This is, for example, the potassium cathode. The threshold wavelength is 0.54 micrometers. This potassium cathode is illuminated by a monochromatic radiation of wavelength 0.48 micrometers. In the first question, will the photoelectric effect take place? To answer this question, we check whether the wavelength of radiation is less than the threshold wavelength. Note that lambda is less than lambda 0. Then the photoelectric effect will take place. The photoelectric effect will take place. In the second part, part B, which aspect of light is shown evidence here? The corpuscular aspect. Which aspect of light is shown evidence here? The corpuscular aspect. That is to say that light is considered to be energy packets or photons. In part 2, calculate the energy of a photon of this radiation. The energy of the photon is given by a certain formula, which is E of the photon is equal to H nu. Nu is the frequency of the radiation. This is equal to Hc over lambda. From the given, we can get the values 6.63 times 10 exponent negative 34 times 3 times 10 exponent 8 over 0.48 times 10 exponent minus 6, and the answer is 4.143 times 10 exponent minus 19 joules. Now we can convert this value into electron volts even though it is not necessary. Note that 1 electron volt is equal to 1.6 times 10 exponent minus 19 joules. Hence, to convert into electron volts, we divide by 1.6 times 10 exponent minus 19. And as a result, the answer is 2.56 electron volts. In the same question, we also have to find the work function of potassium. The work function of potassium is W0. We have the threshold wavelength, so we apply the formula of W0 equals to Hc over lambda 0, which is similar to the energy of the photon. W0 equals to 6.63 times 10 exponent minus 34 times 3 times 10 exponent 8 over 0.54 times 10 exponent minus 6. And the answer is 3.7 times 10 exponent minus 19 joules. To convert into electron volts, we divide by 1.6 times 10 exponent minus 19. So the answer becomes 2.3 electron volts. The photoelectric effect occurs when the energy of the photon is greater than the work function of the metal. Notice that 4.143 times 10 exponent minus 19 is greater than 3.7 times 10 exponent minus 19 joules. So the energy of the photon is greater than W0. In part 3a, deduce the maximum kinetic energy of the ejected electron. The photon reaches an electron in the metal. The metal, this is the electron on the surface of the metal. The metal having a work function of W0. The photon gives all its energy to the target electron. Then the energy of the electron becomes equal to the energy of the photon. E of the photon is equal to a part of the absorbed energy is used to liberate the electron from the metal, that is W0. The remaining part transforms into a maximum kinetic energy of the electron. Therefore, the maximum kinetic energy of the electron is the energy of the photon minus W0. This is equal to 4.143 times 10 exponent minus 19 minus 3.7 times 10 exponent minus 19. The result is 0.443 times 10 exponent minus 19 joules. This is the kinetic energy that the electron leaves the metal with. The electron leaves the metal with a maximum kinetic energy equal to the value that we just resulted in. Calculate the speed of the electron. The kinetic energy of the electron, which is a particle, is equal to half mv squared. The electron will leave the metal with a maximum speed. The speed is equal to radical 2 ke maximum over the mass of the electron. We substitute the values. And the result is 3.11 times 10 exponent 5 meters per second. Note that the speed of the electron can't exceed the speed of light in vacuum, that is 3 times 10 exponent 8 meters per second. So our answer is accepted.